package?
Yep. Yep, it's in the digital package. All right, so here's what we're going over today. We are going to start Unit 3 on circular motion. So everything in this unit has to do with something moving in a circle. So there won't be so much of the, sum of all forces and all of that kind of stuff, although Newton's second law still plays a part here, okay, but not in the same way that it played a part before. Okay, so we're going to be looking at all this stuff to do with movement in a circle, how movement in a circle is achieved, why it is maintained, what kind of things can cause something to move in a circle, okay, that kind of stuff. Now, this does tend to be the easiest of the 4 units. It's also the shortest of the 4 units. Okay? So like a week from now, I'll be telling you when your unit exam will be. Okay? Like it's literally that short. Okay? I usually teach it in about 3 to 3.5 weeks. Okay? So it won't take us very long to get through it all. Now, so key points for today. Understand what circular motion is, understand how it happens, and the relationship between period and centripetal velocity. All right, 2 new terms. Period. Period is the time for one cycle. Okay, that is the technical definition of it in physics. Okay, now what we mean by one cycle in this unit in particular is one rotation or one revolution of the circle. Okay, so the amount of time it takes the object to make one orbit is the period. Okay, so Earth's period is 1 year. It's actually 365.25 days. Why do you think we have a leap year every 4 years? Got to make up for that quarter of a day. Okay, so the next time somebody's spouting off about 365 days from now, you'll know 365.25 days from now. It would be a year later. Okay? All right. Now, this word, centripetal. I usually have people tell me, Mr. Coderre, you're saying that wrong. It's centrifugal, but it's not. Okay? Those are 2 different things. Centripetal and centrifugal, or centrifugal, are different. Okay? People in normal society treat them like they're the same, but they're actually opposites. Okay? Centripetal means center-seeking. A centripetal force is always directed towards the center of a circle. Centripetal forces are the things that actually make circular motion happen. The only reason something moves in a circle is because something is constantly pulling it in that direction. Centrifugal means center fleeing. Okay? It means to go the other way. Okay? And people always use this with force. They go, oh, there's a centrifugal force. There's actually no such thing as centrifugal force. There is no center fleeing force. Okay? That is trying to take things out of a circle. If there was, things wouldn't move in a circle. Okay? So there's no such thing as centrifugal force. Now, usually at this point, people go, well then, why do I feel like when my friend turns a corner too fast, like I'm going to fly out of the car? Or if he has a Jeep with no doors, I actually fly out of the car. Okay? Why is that if there's no centrifugal force? Well, that's not a force. It's inertia. Okay? If I turn a corner really fast, like this, okay? Which direction does my inertia want me to go? Think about it. Last time you turned a corner when it was icy, what did your car do? Slide. Tried to go straight because of its inertia. That's not because of a force. There's no force grabbing your car and going, come out of the circle. Okay? It's not trying to pull it that way. Okay? It's just your car's inertia. Newton's first law says, in the absence of any forces, an object will travel at a constant velocity along a straight line. And that's what your car is trying to do. Okay? The same thing is true, okay, if you're whirling something around and around in the air. Like this, okay? If I'm whirling this thing around and around the air, and I let it go,
Oh, please don't.
which way is it going to go? Well, it depends where I let it go. If I let it go when it's coming around this side of the circle, it's going to go that way. If I let it go here, right in front of me, it's going to go that way. I'll demonstrate. Probably. Okay? I let it go right here. It went in a straight line. Okay? It didn't try to go that way. It didn't try to go straight out of the circle. Okay? It went straight. Right? Lots of actual stuff works on that, like shot put works on that. Discus even more.
Oh yeah.
Yeah, because most now shot put is also a spin. People have developed
Shot
that.
puts this one.
This one,
Oh,
yeah.
yeah.
But there's actually, if you watch the Olympics now, a lot of the shot putters actually spin. Okay, with shot put, they never used to, but they do now. Discus, they spin. Okay, so they do let it go here, right? Okay, the same idea. You're building up angular momentum. Okay, you're building up centripetal force. You're holding the discus from leaving the circle until you want it to. And when you do, it goes straight.
I don't know what it's called, but didn't they do that around one of the planets to get it out from outer space?
Exactly. It is exactly how the gravity slingshot works. So if you've seen The Martian, it's one of the maneuvers that they use to accelerate the Hermes, the ship that goes back to get him. They use the moon, the Earth as a gravity slingshot. We get all of our spacecraft to deep space that way. Okay? We actually, for a lot of them, we actually send them towards the sun first. Okay? Let the sun's gravity pull them towards the sun, and then usually use Venus as a gravity slingshot to send them out the other way.
Is that like in Apollo 13?
Yes, Apollo 13, same thing. They use the moon to accelerate them and fling them back towards the Earth. Yeah.
What did we say was like a softball pitcher too?
Exactly, yeah. So with the windmill pitch, same idea, yeah. Okay, you get that thing going around and around. You can get that going a lot faster than you can with a, right, well, unless you have good technique, right? But yes, with a softball, big and heavy, you don't want to throw it like this because you wreck your elbow. Okay. Yeah, so the whole idea of this is how we build up, okay, how we build up all this extra speed. Okay, a lot of primitive weaponry also revolved around this idea. So if you've ever seen somebody with the chain mace, okay, so they got like the stick in their hand and they got the big spiked ball on the end of the chain, they're rolling it around. Actually, a completely impractical weapon. Okay, it's like they use it all the time to look really intimidating. But when was the only time it could hurt you? When it was close to you. It spent like 3/4 of the time away from you. Okay, you could easily get inside, okay, of that if somebody was using one. But yeah, that's how that would work. You could get that going way faster. It's also how David slew Goliath. Okay, the sling. He didn't throw a rock at Goliath. Okay, that would have probably not killed Goliath and would have just made him angry. Okay, but instead he had the sling, which is just a little piece of like a strap, basically made out of hemp. Okay, and he just whirled it around really, really fast, and then at the right time, lets it go. Okay, and when he let it go, it flew out at a very high rate of speed, far faster than he could have ever thrown it himself, okay, and had enough force to essentially fracture Goliath's skull. Okay, I think I have a video on that, which we'll watch in a little bit, actually. Okay, that's how it works. Okay, so uniform circular motion, okay, is the motion of an object traveling at a constant or uniform speed on a circular path. Okay, why do I emphasize speed? Something moves around and around in a circle, okay, it's traveling at a constant speed. Why do I not say constant velocity? Right. Its velocity is not constant. The magnitude of its velocity is constant, but what's always changing? Its direction. In order to move in a circle, this object has to always accelerate. Okay? It may not be going faster, but it's always being pulled towards the center. The only thing that keeps this in a circle is the fact that there's a string attached to it that I'm holding onto. I'm exerting a force through that string, pulling the tape back towards the center. That's why it keeps changing direction. When you go around the corner in your car, friction keeps you in the corner. Okay? It actually pulls the car back towards the center, which is why when it's icy, you go in a straight line. That centripetal force is not there. Okay? Friction isn't present, so you follow Newton's first law. There's nothing to pull you towards the center. Okay? All right with that idea? All right. Same is true with like merry-go-rounds. Have people ever been on a merry-go-round? Okay, just so you know, your generation has like a really disappointing childhood because your merry-go-rounds suck. Okay? Because they're safe. Yeah. They got nets around them so you can't fall out. When we had merry-go-rounds, when I was a kid, they didn't have anything on them. And you'd spin them really fast and see who came off first. Okay? My wife actually, a friend of hers lost his hand because they were doing this and they had tied themselves to the merry-go-round. And yeah, pulled it right off. Yeah, okay, yeah. Yeah, pretty scary stuff. Okay, now, just so that we can have a little bit of fun, I do want to show you this video of morons and merry-go-rounds. Okay, because it's kind of interesting. Okay, so they are all moving at a constant speed, but not at a constant velocity. There's always an acceleration.
Is this like the same thing as like when you're like spinning a circle and you have your arms out and then you like pull them in and you spin faster?
Similar. That's an angular momentum thing as opposed to still circles, but it's about conservation of momentum. So when you have all of the mass concentrated in the middle, the momentum is more easily conserved than when it's spread out. Right? So if you ever like figure skating when they tuck in like this and they can spin really fast and they go like this to slow down, they're spreading out mass beyond the center, which slows their. Right? The momentum is still conserved, but because the radius is now larger, they slow. Okay. All right. So we got that plane, which is like the tape I had going around and around in a circle. Okay, being pulled towards the center, constantly accelerated towards the center by that centripetal force. Okay, but the velocity vector we can see in that diagram is always changing, okay, because it's always going a different direction, being pulled towards the center. Okay?
We are like a field trip to
No, unfortunately we can't. There's a lot of liability issues now that you know all this stuff.
Oh, right.
That's why we don't.
Can we go to the parks?
We used to go to like the West Edmonton Mall, but they started ripping us off real bad and COVID, a bunch of people on the bus together. Yeah, kind of wrecked it. Okay, so when we're calculating the speed at which something is moving through a circle, okay, we use a formula that we're quite familiar with. This one. Now, you're probably looking at that and going, Coder, you've never seen that before. Okay, but you have. What does 2 pi r calculate? Circumference. Okay, 2 pi r calculates circumference. And big T is the time it takes, the period, the time it takes for one complete cycle. So really, phi equals d over t. It's just applied to a circle. The distance you travel is the circumference of the circle. The period is the time it takes to go around the circle one time. Phi equals d over t. So we're going to use that formula a lot in this unit, okay? Simply because we are dealing with something traveling at a constant speed when it's going around and around in a circle, at least in uniform circular motion. Okay? Later on in the unit, we'll be going over non-uniform circular motion, which is vertical. Okay? So what we're going to deal with in the first half is just this. Something moving around in a horizontal circle, its speed is constant. But if I make that circle vertical, right, gravity plays a part. So where's the mass now moving the fastest? The bottom, right? Okay, it goes very slow at the top, quite a bit faster at the bottom. So that's not uniform. Okay, we're going to start out with uniform. Okay. So one of the places where we see this kind of put into practice, or put to use, okay, is with a tire balancing machine. Okay? Probably most of you have recently had your winter tires put back on. Okay? And whenever they put tires on a rim, they have to balance them. The reason they have to do that is the process by which tires are made doesn't distribute the material perfectly. Okay? They basically just pour molten rubber into a mold and then cool it, and they make a tire. Okay? So that doesn't always distribute the rubber evenly. So you might have heavy spots on a tire. And so the person who puts the tire on the rim then puts it on a tire balancing machine, which is on kind of a floating spring. And as it spins, if there's any difference in weight, okay, in that tire, it'll pull the machine in that direction because there'll be more inertia on that side of the tire than the other. And the computer then will tell them, you need to offset this mass on this side with a weight over here. Okay? So it'll stop it right where it needs to put the weight, and it'll tell them how much weight to put there. You can see these on your rim. Okay? They're sometimes on the inside of the rim, so like actually in here, okay? And there'll be like a little metal square, and they'll stick them to the inside of the rim. Or if you've got an older rim that's got a lip on it, sometimes it just looks like a little tag that just kind of sits right here. Okay? And the weight sits there to offset whatever weight is not right on the tire. You can feel this in your car if your tires aren't balanced, or if you've just driven through a bunch of deep snow and some snow gets on the inside of the rim, and then you try and go to highway speed, the weight, that extra mass on one side of the tire, will cause the tire to vibrate. The whole car will shake. Okay? Anyone ever had that sensation? You're driving along and at certain speeds the car will vibrate a little bit, but you get past that speed and it seems to go away. Okay? Well, that's because your tire's out of balance, right? And it's harmonic, so there are certain speeds at which it will occur. Right? If all your tires are out of balance, it just seems like your car shakes all the time. Okay? But if you only have one that's out, then that's what you'll feel. Okay? And usually what you have to do, if it's snow anyways, you have to pull over and get the snow out of the wheel, okay? Because it can be hard to control your car, and it's not good for your suspension either because it constantly chatters. Okay? So that's one of the things that it can be used for. But we're going to use this as an example for using this formula. Now, the other thing we haven't talked about yet is this relationship about period. Okay? Period is the number of seconds for one cycle. Okay? So it's always listed as a unit of time, either seconds or minutes or hours. Okay? But there's something that's like period, but it's its inverse. Yeah. Okay? And that's frequency. Frequency, okay, which is just little f, is cycles per second. So they're the inverse of each other. Okay? And that's why on your formula sheet you have this formula. T equals 1 over f. They're the inverse of each other. Okay? One is in seconds per cycle, the other is in cycles per second. We use cycles per second for like musical notes. Okay? So the frequency of sounds, okay, is usually measured in hertz, cycles per second. All right, everybody okay with how that sets up? Okay, so our formula here is 2 pi r over t, but I could also write it this way. Two pi r times f, because f is 1 over t, and when the formula is written like this, we're really just saying 2 times pi times r times 1 over t, right? So 1 over t is f, so I can just plug f in directly. Depends which one you're being given in the question. All right, so back to this idea. So we've got this wheel that has a radius of 0.29 meters. So they told us what r is. Okay? It's being rotated at 830 revolutions per minute. Okay. Okay, did they just give me frequency or period? 830 revolutions per minute. Is that period or frequency? Period. Nope, frequency. Okay, remember. What are these? Hey, at least he tried. Okay, nobody else said it. Better to be wrong and have tried than to say nothing about it. Okay. Remember, frequency is in cycles per time unit. This is revolutions per minute, so that's frequency. Okay? Period is in time units for one cycle. Okay, so that would have been like minutes per revolution. That would have been period. This is revolutions per minute, so that's frequency. All right, we want to determine the speed, so we got 830 RPMs, okay, revolutions per minute. Right? We want to determine the speed at which the outer edge of the wheel is moving. All right, we know this is our formula. V equals 2 pi r times f. Okay? Now, if I use the numbers I'm given, I'm going to get meters per minute. Is that a usual unit for speed that we use? Okay, so how do I get revolutions per minute to be revolutions per second? Divide by 60 or multiply by 60? Divide by 60. It'd be a lot less revolutions per second than it would per minute, yeah? Should be a smaller number. All right, so 830 divided by 60. Okay, so this thing is rotating at 13.8 revolutions per second. Okay, the tire is going around and around 13.8 times every second, so it's moving fast. Okay, all right, 13.8 RPS. All right, now that I've got that, now I can use this formula here. So 2 times pi times 0.29 times 13.8. Okay, that'll give me the speed at which the outer edge of the tire is moving. Now, when I do this, should I multiply by 3.14 or should I actually use pi? Actually use pi. Really, really important. Pi is a much bigger number than 3.14. Okay? So, hit the pi button. That's second function on the up arrow here. So 2 pi times 0.29 times that 13.8. Okay, so the outer edge of the tire is moving at 25 meters per second. Okay, which is 90 kilometers an hour. So it's moving fast.
What is like the significance of pi? Like what's the point of it in general?
Pi is the relationship between the diameter and the circumference of a circle. So doesn't matter what circle you have, if you divide the circumference by the diameter, you always get that number. Always. Yeah. Okay. Yeah. Somebody along the way discovered that. That's the relationship there. The distance around a circle is always pi times the diameter. Okay. Questions on how that one works? Okay. So really what we need to get out of this is what frequency and period are, okay, that they measure something similar, okay, but that they're the inverse of each other, and how we use this formula, 2 pi rf, or 2 pi r over t. Okay, so that's what we just did. We got 25 meters per second. Okay, so the thing we have to remember about uniform circular motion is that the magnitude of the velocity vector is constant. Okay? Yes, that object's going to go around and around in a circle. That's more circular than that. Okay? But it's going to go around and around in this circle, but the direction that arrow points is always going to be tangential to the circle. Okay? It's always going to point kind of 90 degrees away. Okay? Tangent to the circle there. So the direction's not constant, but the speed is. Okay? And if the velocity's not constant, then there's an acceleration happening. That's kind of the big thing here. Okay? Acceleration is any change in velocity. That's the definition of acceleration. The magnitude of the velocity doesn't have to change for that to be true. All that has to change is the direction. Okay? So when I make something go around and around in a circle, it's traveling at a constant speed, but is constantly accelerating. Okay? That acceleration is being caused by a force that is pulling it towards the center of the circle. Okay? Now, if it's always accelerating towards the center, why doesn't it go towards the center? Yeah, it's inertia. Okay? It balances out. Okay? That's how you get something to go around and around in a circle. It's how we make satellites orbit the Earth. Okay? The only thing you have to do to make a satellite orbit the Earth is make it go fast enough that the distance it falls, because gravity is accelerating it, is balanced by the distance the Earth curves away. Because by the way, the Earth is round. You can shake your head all you want, but the Earth is round, okay? And if you're a flat earther, that's just dumb, okay? Sorry, there's no nice way to say that, it's just dumb. Okay? We know the Earth is round, okay? It has to be round. We've been to the moon and looked back at it, it's round. Silly flat earth people. Okay, so. Yeah, it's just spinning, so like they got all kinds of, yeah. Yeah, you can't convince people. It reminds me of this saying, never argue with an idiot. They will drag you down to their level and beat you with experience. Okay, so to get something to go around the circle, essentially we have to balance how fast it's going with how much it's accelerating towards the center, okay? And that's how, again, we get satellites into orbit. That's a whole nother lesson. Oh, I just said whole nother. That's a whole other lesson, because that's not a real way to say things. A whole other lesson, okay, in this unit, okay, how we get things to orbit here. All right, so the acceleration of an object towards the center of a circle can be calculated if we know how fast the object is going and the radius of the circle. All right, so we would square the speed that it's moving around and around at and divide it by the radius of the circle, and that'll get us the centripetal acceleration. Now, if we're looking at this formula, v is squared in this formula, which means any change in v is going to cause what kind of a change in a? An exponential change in a. Okay? This has big repercussions for safe driving. Right? When you take an exit ramp, okay, like the one out here to get onto Highway 2, okay, it's a banked curve, which we'll talk about another day. Okay, but it has a recommended speed. Okay? That recommended speed is based on the radius of that corner and the angle at which it is banked. If you take that corner at that speed, your car will stay in the corner, even if it's covered in ice. Okay? That speed is safe because of the nature of that curve. If you go faster than that, you are now relying not on the bank of the curve, but on the friction between your tires and the road. If it's really icy, then you will fly out of the curve. If you are overcautious, you will fall in to the curve. Actually seen it happen. Okay? Somebody was just being overcautious. They came into this corner, and I was watching it happen, and being a physics guy, I'm like, oh, damn it, speed up, please. There's nothing you can do. Okay? I just wanted them to please go faster so that I didn't slide into the swamp that was in the middle of the corner. So I actually had to speed up a little bit and let my car slide slightly out in order to get around them as they slid into the middle of the corner, because they went slower than the recommended speed. So you have to be mindful of, okay, any change in velocity is going to require exponentially more force to keep you in it. Okay? So if I take that corner instead of at 60, which is the posted speed, okay, if I was to take it at 120, which would be crazy, okay, but if I did, I would require 4 times the amount of centripetal force than I would at the recommended speed. Not twice as much. I'm only going twice as fast. But because this has an exponential relationship, I will need 4 times as much force to keep me in the corner. And there's not too many tires, okay, that are suddenly going to magically produce 4 times as much friction as they did before.
Is that why like the NASCAR tracks are super steep?
It is exactly why NASCAR tracks are so steep. Okay, they're banked really steep. And in fact, when they pave them, they have the paving machine held on by a crane. So they have a crane parked on the outside with a long arm that reaches over and holds the paving machine on the track, because it would slide in if it didn't, or tip over. Okay? Yeah, so they have to actually hold it on. Okay, is that making some sense? All right, so when we do this, obviously we've got meters squared per second squared, and we're dividing that by meters, which of course leaves us with meters per second squared, which is the units for acceleration, so that formula works out, okay, the way it's written. Centripetal acceleration is speed squared divided by radius, okay, and that'll tell us that, okay? And force works the same way. Centripetal force is mass times v squared over r. In other words, mass times acceleration. Still Newton's second law. Okay, just applied now to a circle. Okay. All right. What are some ways you can make a turn that could make the turn easier? There's two things you can do to make the turn easier. Take it wider or slower. Right, there's two things. Now look at this formula. Okay? This can't change. I mean, I suppose you could toss mass out of the car along the way and change the mass. That actually wouldn't help. You would actually want to toss mass in, okay, if you wanted to more successfully navigate the corner. Okay? But if you slowed your speed, it would be easier to take the corner. Or if you took the corner wider, you'd be dividing by a bigger number and require less centripetal force. Okay, we intuitively know those two things. Okay, going around a corner, either I slow down or take it wider. Okay, that's why race car drivers, okay, will try and do this. Okay, rather than follow the corner completely, they'll usually come in kind of high and exit a little. I didn't draw that very well, but they'll exit a little higher. So they come in high on a corner like this, and then they exit lower down in here, okay? Essentially taking this radius and making it that radius, okay? They make the circle bigger by starting on the outside and coming to the inside. Essentially, they flatten the corner out, making it a wider circle, okay? That's why they always take that kind of tack. So if you've ever seen any Nascar, that's why they do that. They're all right against the wall, and then they're right against the inside, and then they're out against the wall on the outer end again. All right. Am I good with that? Okay, we're going to leave it there for today. Okay, talk about centripetal force, and I'll show you the David and Goliath thing.